the next idea is to do a small experiment. So I have once again here my multimeter. I can already switch it on to measure resistances, and I have two small breadboards. And so now the idea is to do this, if we check the lecture slides, to show that these formulas that we have used here for the star delta conversion and for the delta star conversion, that they work and that we can also have them prove them by a measurement, by some experiment. So remember, for the star delta conversion, we did something that, let me go to full screen mode here, Seitengröße, yeah, this looks good. Okay, yeah, so for the star delta conversion, we always checked the resistance between one terminal and two other short circuited terminals. And so then the resistance measured in the star should be the same resistance as measured in the triangle. And the idea here was, if we short circuit these two nodes 2 and 3, for example, then this resistance will be eliminated and we have just these two resistances in the formula left. And so then we got this system of equations with three equations and three unknowns, and we could somehow solve this one. And the idea of short circuiting this node was, okay, then on the right side of this equation system we always have just two of these resistances or conductances, and then it was easier to solve. And the same approach we also used for the delta star conversion, but here we always left one terminal open. We calculated, or we checked what is the resistance, equivalent resistance between node 1 and 2, for example. On this side, then it was fairly complicated, but on this side, if this is open, there's no current through this resistor, no voltage drop there, so we just have the series connection of the two. And this is what I would like to show in a small experiment. So let's assume that we have a star circuit with 3 resistors, and of course we need to have certain values for them. And the star does not look too nice, but okay. And so the 3 values, let's call this 1, 2, and 3, these nodes, is that this resistor R1 is 1 kilo ohm, that this resistor R2 is 2 kilo ohms, and that this resistor R3 is 3 kilo ohm. And yeah, so let's build up this circuit, and I will use yellow. I don't know if I have yellow here. Yeah, I have yellow, so we will use yellow for the star. So the yellow breadboard is the one that contains the star circuit. And so I need to have 3 resistors. And so here is my box with the 1 kilo ohm resistor. So I will take, once again, one resistor out of this box and already somehow connected to this yellow breadboard. And we can measure the resistance of this, and then we see, okay, it's not exactly 1, but 0.998. Okay, we could note down this value, but I think we will just stay with the 1. So then here's my box of 2 kilo ohm resistors, and I will also take a resistor out of this box and try to connect it that we get this, we get something that looks like a star in this case, but oh no, the 2 was connected to the other side. So this is the resistance R2, and I can also measure the individual resistance of this resistor. Oh, and this is not 2, this is something more. This is 2.1 something, so then this resistor is inside the wrong box. So, but this should be a nice 2. Okay, this fits. This is 2.0 something. Okay, and so then finally I need to have a resistor out of my 3 kilo ohm resistor box and also connect this one to the circuit here. So now we already have a nice star circuit, and I can also measure the equivalent resistance of this, and this is 3. Okay, so this fits. So now we can try to do these cases and say if we leave something open, so in this open case, the resistance between nodes 1 and 3, the resistance between nodes 1 and 2, and the resistance between nodes 2 and 3 should be, if we measure between 1 and 3, how large should the resistance be? 1 plus 3, so it should be 4 kilo ohms. If we do it from 1 to 2, it should be 3, and here it should be 5. Okay. I don't know. Somehow it's not drawing nicely. Okay, now it works. Okay, and so in this short case, so if we go from 1 to 2 and 3, let's maybe write it like this. Yeah, so we have 2 in parallel to 3. This is yeah, 6 over 5. So it's 1.2 plus 1 should be 2.2 kilo ohms. So then if we go from 2 to where 1 and 3 are short circuited with each other, so if we go from here and now these two are connected with each other, so then we have 1 in parallel to 3 is 3 over 4, and this is 0.75, right? 3 over 4 plus 2 should be 2.75 kilo ohms. And if we measure from 3 to 1 and 2 are short circuited with each other. So if we are measuring from here, these two are connected with each other. We have 1 kilo ohm in parallel to 2 kilo ohm. Is 2/3 plus 3 is should be 10/3 kilo ohm, and this is 3.3 kilo ohm, right? Okay.
So sure of the first one?
Am I sure of the first one? 2 over 3. No, 2 parallel with 3. We can check in Octave. So if I move this to here, so this R13 that we measure there. Yeah, okay. We will just calculate like this. So it should be 1 plus the parallel connection of 2 and 3. And this is 2.2.
Yeah. 1 plus, yeah.
So this works. Okay, so now we can try this in the experiment. So I will make the window here a little larger. So this is my star connection in the very same way. And so now if we measure the things on the left side, if I measure between 1 and 3, we get 4 kilo ohms, fits. If I measure between 1 and 2, we get 3 kilo ohm, fits. If I measure between 2 and 3 in the circuit, we get 5 kilo ohm, also fits. Okay, so then if we are on the on the right side, if I measure between 1, which is this node, and now I need to have another wire to do a short circuit between here and here. So this is the short circuit connection. And now I measure to the other node. And so we get 2.2, which nicely makes sense. So then if I do a short circuit between 1 and 3 and measure against node 2, now we get 2.76, which also makes sense. And so now if I do the last connection, do this short circuit here on this side, and measure between here and this short circuit, then we get we get something. Yeah, and the calculation is wrong, right? It should be 11 because, yeah, it should be 11, and that's why we check. That's why you always do a measurement. Yeah, so here we said it was 2/3 plus 9 is 11. Plus 9/3 is 11, and then it's 3.66. Or 3.6, or 3.7, let's say 3.67 kilo ohm. And this is also what we measure here. Okay, so this perfectly makes sense now. So now the next step is to convert the star into a delta. And so I need to draw a new circuit, but of course we still have the same nodes 1, 3, and 2. And we have resistors in a delta connection connecting these nodes with each other. And I will call these resistors, of course, R1, 3. It's not the same as here. R1, 2 and R2, 3, or maybe I should give them another index delta, that it's now the resistors in this delta circuit. And yeah, the first thing now would be, okay, we need to have the values of them. So the R1, 3 delta, yeah, how could they be calculated?
Like 1 plus 3 plus 4 divided by 2, so 6.
Yeah, okay, this was too fast for me. So I would once again go back to this formula here. So we want to do this star delta conversion, so we need to have this formula. And so if we want to have a resistance connecting these two nodes, it's the sum of the two and then the product divided by the other one. So if we want to have this one, it's the sum of these two, so it's 1 plus 3. and then, so this is 4. Yeah, so it's 4 kilo ohms, and then plus 1 times 3, and then divided by 2. So this is 3 divided by 2, so 3 divided by 2 kilo ohm. And so then we end up with 5.5, right? So we get 5.5 kilo ohm. Okay, so then the next one are 1, 2 delta. This one here is the sum of these two. This is 2 kilo ohms. Okay, 3 kilo ohm. Yeah, I was always already with the product. So 3 kilo ohm, and then plus the product divided by the other one. So 2 over 3 kilo ohm. And this is what I think what we have here, right? So this is should be 11 over 3 kilo ohm, or 3.66 kilo ohm. Okay, and the last one, R2, 3 in the delta connection, is the sum of these two. This is 5 kilo ohm, and then plus the product of the two divided by the other one. 2 times 3 is 6, so 6 kilo ohm. And we end up with 11 kilo ohms in this circuit. Okay, so we need to have a 5.5 kilo ohm resistor, a 3.6 or better 3.7 kilo ohm resistor, and an 11 kilo ohm resistor to build a corresponding delta circuit that behaves the same way. So luckily in my box here I have not 3.7 but 3.6 kilo ohm. So at first I will, so this was our star. I will put it on this side here. Now I have another breadboard, the orange one, for the delta. And so we need to have this resistor with 3.6 kilo ohm. And if we check, so now for this I will use the orange breadboard. And the 3.6 resistor was this one here that was connecting 1 and 2. So it should be in this direction. So I will put it like this on the breadboard. And measure this resistance individually. And then you can see it could be a little more, but okay. I did not have a 3.7, just 3.6. Okay, so this is the first resistor. Then we need to have 5.5, and 5.5 needs to be connected on this side here. So luckily in my box I also have 5.5 kilo ohm resistor. And this one needs to go to this side here. And this is what I can also still measure individually. Yeah, and then it's, as you can see, it's also not perfectly 5.5, but more 5.6. But okay, still should somehow work. And then the last thing that we need is this 11 kilo ohm resistor that we have here. And in my box, of course, I've also prepared so here the label is upside down, but there's also 11 kilo ohm And before connecting this, I will measure the 11 kilo ohm resistor individually, and there you can see, okay, this is also not perfectly 11, but something like this. And the 11 kilo ohm resistor should be the one that is the lower leg there, let's say, of the delta. Okay, so this is now the delta circuit, and so now we can try to calculate the same stuff as before. So if we do this open case and measure R13, the resistance between here and here, what should we get? At the end, we should get the same 4 kilo ohms as before. But we should get the series connection of these two, and then this one in parallel. So if we try to calculate this with Octave quickly, so in this case we should get the 3.66 in series with 11, and this in parallel with 5.5. So we should get the parallel connection of 5.5 and then 3.666 plus 11 in series. So this gives 3.9 something. So this should be 4 kilo ohm once again. So of course here in this case R12, between these two, now here should be the 3.66 and here should be the 5.5 kilo ohm, and if we connect them in parallel, we should get something like 3, and it fits. So here we should once again get 3 kilo ohms. And for the last one, R23, so now we have the 11 here and the 3.3 here at the end. And this parallel connection gives us approximately 5 kilo ohms. And this should of course be the case because this was exactly our approach for deriving these formulas for the conversion. So if we go back and check, so this is still our very same circuit as before. So if I measure between 1 and 3, which were these nodes here, then I get the 4 kilo ohms. If I measure between 1 and 2, I get 3 kilo ohms. If I measure between 2 and 3, I get 5 kilo ohms, which nicely works, even if the resistors were not perfectly accurate in comparison with what we calculated individually. And so if it works like this, then of course it also works, or it should also work in this short circuit case. So in the short circuit case, if we once again do this R1, 2 and 3 short circuited, so now these two are short circuited and we are measuring the equivalent resistance between 1 and here. So now what should we get? What should be the equivalent resistance? Just the parallel connection of these two, right? So the parallel connection of 5.5 and 3.66, I think this is something that we had here before. So it's these two values, but now just the parallel connection. And then we get, yeah, and I should probably better use 3.66. Okay, so then we get something like 2.2 kilo ohms. Also what we had before. If we take a look at this equivalent resistance between node 2 and 1 and 3 short-circuited, then now it should be the parallel connection between these two resistors. This is the 3.6 kilo ohm and the 11 kilo ohm. So 3.66 and 11 gives, yeah, 2.75. The same what we have calculated here. And the last thing between 3 and 1 and 2 short-circuited. So these are connected with each other. We are measuring between here and here. So now these two are in parallel, which is this one and this one. So 5.5 in parallel to the 11, and then we get once again 3.66. And so this is what we can finally also check in the experiment. So I need to have, this was the star circuit, this is the delta circuit. Now I need to have another short circuit connection and measuring the equivalent resistance between 1 and 2 and 3 short circuit to each other. And we get little less than 2.2 kilo ohms, which makes sense. So then the next was measuring between 2 and 1 and 3 short circuited. So now 1 and 3 are short circuited. I'm measuring between node 2 and the other node here on this side. And we get something like 2.7, which also makes sense. And so now I'm changing the short circuit from node 3 to node 2. And we are measuring the equivalent resistance between 2 and the other two short-circuited nodes, and we get something 3.7. Yeah, and this is, so this perfectly works. And this is also the way how this star delta conversion formulas that we now have used just in the one direction. We could have also used it in the other direction around, but what was the approach here to derive them with the short circuit between two terminals, and for the open circuit case that was used for the derivation of these formulas.